My dear student friends, I hope you are doing well. Now we are going to discuss about the diffusivity, and in the last class we were discussing about how to calculate the flux, what is the continuity equation, and what is your Fick's law, and what your Fick's law says your mass flux or the molar flux is proportional to the concentration gradient, and that proportionality constant, what we said, is the diffusivity. And the diffusivity is designated as DAB, where J is equal to minus DAB into dCA by dZ, and where the proportionality constant, we called it as a diffusivity, and this diffusivity is the most important property for the estimation of the molar flux or the mass flux. And already we have seen about different situations, that is a non-diffusing B, or maybe about the equimolar quantity diffusion. In the case of non-diffusing B, when I take a system consists of A and B molecules, only the molecules of A is moving from one location to the other location, whereas the B molecules are not moving. In the case of equimolar quantity diffusion, I have a system, the system contains A as well as a B. A is flowing in the one direction, the B is flowing in the opposite direction. And in the case of equimolar quantity diffusion, if 1 mole of A is moving in one direction, 1 mole of B is moving in the opposite direction, then your Na by Na plus Nb is going to become Na is equal to minus Nb, so Na by Na plus Nb is equal to 0. And what we did is we tried to derive an expression for the calculations of Na for the equimolar quantity diffusion. We have tried to derive the equation for the calculations of Na for the non-diffusing P case. And if you observe that equation, and if one has to calculate the flux, the most important property, that is nothing but diffusivity, and without a diffusivity one cannot do the calculations of the fluxes. And particularly when you talk about the gaseous systems, and a lot of diffusivity values are available in the literature. There is a book by Kessler where we can see how diffusion is going to take place, what is the diffusion coefficients. And for a gaseous system, so the diffusion coefficient is in terms of 10 power minus 1, is in the order of 10 power minus 1 centimeter square per second, or that is nothing but 0.1 centimeter square per second. And for many of the gases, the diffusivity of component A in B, many of the gases it is available. If the diffusivity of the gases are not available, then what one has to do, one may have to use either theoretical expression or maybe some empirical expression or maybe a semi-empirical expressions one has to use, and we have to calculate the diffusivity values. And one of the empirical equation or one of the theory that people were using is a equation which is based on the kinetic theory. People have proposed an equation which is based on the kinetic theory, and this kinetic theory has proposed by the Chapman and Emsky. And this kinetic theory, what the kinetic theory says, this, according to the kinetic theory, there is a strong interaction between the molecules and the molecules, and we have a one parameter called as the Lennard-Jones potential. I don't know how many of you know about this Lennard-Jones potential. If you are not aware of this Lennard-Jones potential, just you can go back to the chemical process calculations and you look at the vapor pressures. That is, you take the book of Augen and Watson and you take the vapor pressure chapter, that is the introductions of the vapor pressure chapter. We are going to find this sort of a graph where it is going to show us like this. So this is what we call it as a Lennard-Jones potential. Do you know it or not? If you are not knowing about this, it is so simple to explain. Like when you are very far away, that is when you are not joined in the college, you are not knowing each other, that means your distance of separation is very high, and once the distance of separation is very high, we have some, when you talk about molecules or when you talk about the human beings, always there will be some attractive forces and there will be repulsive forces. And when you are not knowing each other, that is the distance is very large, generally the repulsive forces will not come into the picture, only the attractive forces comes into the picture. So this attractive forces minus repulsive forces is some sort of a maybe repulsive forces minus attractive forces that is given by some sort of a pi AB is equal to epsilon AB into 1 by r to the power of 12 minus 1 by r to the power of 6. This is what we call it as a Lennard-Jones potential, or this is what you call it as Chapman and Ansky has proposed a theory. This is the repulsive forces, maybe this is the attractive forces. So these attractive forces are very, very dominating. When the large distances are there, then this is the negative. But as you are coming in closer and closer, that is after once if you join in the college, you are now you are knowing each other, and still you have some distance of separation. When you have a distance of separation, you are attracted each other. So that means when you take a repulsive forces minus attractive forces, the repulsive forces are less compared to the attractive forces. The net is going to become negative. When the net is going to become negative, this is going to be decreasing. And now because of this, what will happen? Now attractive forces are further increased. Further there is attraction. Now you are coming more closer and closer. And a situation comes, you may be sitting in the same chair or maybe same table, and that means you are coming and closer and closer, and you are sitting in the same table. There the attractive forces are very, very high compared to the repulsive forces. Ultimately you have some net energy. The net energy is going to lead to some minimum energy that we call it as a epsilon AB, and this distance we call it as a R minimum. Now what will happen? Suppose if you reduce further distance between both of you, then what will happen? You are knowing each other very well, you know the drawbacks of others, then the repulsive forces are now dominating compared to the attractive forces. The net energy is going to become positive, and it is going to become asymptote to your y-axis, where the y-axis is nothing but what you call it as your potential energy. And this is what the theory which is given by the Lennard-Jones potential. The same theory can be applied for the molecules also. When the molecules are very far away, they are not knowing each other, the attractive forces are more compared to the repulsive forces. But when they are coming closer and closer, and when the distance is some distance that we call it the minimum distance, the net energy that is nothing but attractive energy is larger. That is what we call it the minimum energy. Now if you reduce further the distance, the repulsive forces are going to be dominating more compared to the attractive forces. This is going to become as asymptote to your y-axis. So this is what your Lennard-Jones potential is going to tell you, and there are two parameters, that is what we call it as the epsilon AB, that is what we call it as the R minimum. Based on this, the Wilkie and Chang have proposed an equation, or what we call it as the Wilkie-Lee equation. According to the Wilkie-Lee equation, this is nothing but the diffusivity of component A in B is equal to 10 power minus 4 into 1.084 minus 0.249 square root of 1 by MA plus 1 by MB t to the power of 3 by 2 multiplied by square root of 1 by MA plus 1 by MB, whole divided by PT RAB square into f of KT by epsilon AB. So this is the equation one can use to calculate the diffusion coefficient of A in B, and this is the equation which is given by the Wilkie-Lee, and where you know this MA and MB are the molecular weights, and this temperature T is in degree Kelvin, and P is the pressure in terms of Newton per meter square, T is in degree Kelvin, and P is in Newton per meter square. Then we have RAB, molecular distance between the molecules of A and B, that is given by RA plus RB by 2, which is in terms of nanometers, and the diffusivity DAB is given by meter square per second. Then we have molecular weights MA and MB, that is nothing but kgs per kg mole, and here we have epsilon AB, energy of attraction, that is what I told you. These are the parameters of your Lennard Jones potentials. This is nothing but epsilon A, epsilon B, then this f of kt by epsilon AB is a collision function which is going to depend on the kt by epsilon AB, where k is the Boltzmann constant. So now if I know the temperature, if I know the pressure, if I know the molecular weights, and if I know the Lennard Jones potential constants, then one can estimate the diffusion coefficient of component A in B, and this equation can be used for the calculations of your diffusion coefficients. Now the question is how to calculate this collision function, and this collision function we have a kt by epsilon AB. You know how to calculate the epsilon AB, and you know epsilon AB is equal to epsilon A and epsilon B, and we can take a geometric mean of epsilon A and epsilon B to get epsilon AB. Then one can calculate the kt by epsilon AB, and this kt by epsilon AB, you know k is equal to Boltzmann constant, you know the value of that, temperature T is known, epsilon AB is known, and kt by epsilon AB we have on this thing, and on the y axis we have a f of kt by epsilon AB, and we can find, you can take any book on mass transfer operations, we can find these collision functions, and maybe this is the 2 axis, this is the 1 axis, we can read from this here, this is we can read it from here, and only the scales are different. So once if you know the kt by epsilon AB, one can calculate the f of kt by epsilon AB, and this RA and RB molecular radiuses, and this molecular radiuses if you can calculate using a formula, if it is known, it's known, otherwise we can calculate as 1 by 1.18 into v to the power of 1 by 3, and where v is nothing but atomic volume or the molecular volume, and this molecular volume we are going to calculate from atomic volumes. So that is, now if you know the structure of the molecule, each molecule contains so many atoms. If you know the number of atoms, and we can use your group contribution method for the estimations of molecular volume. Once if you know the molecular volume, we can calculate the molecular radius, R value you can calculate, and we can calculate epsilon by k. The values of epsilon is given for many of the substances. If suppose if these values are not known, and one can use this empirical equation 1.21 into Tb, where Tb is the normal boiling point temperature in terms of degree Kelvin. So if you know that normal boiling point temperature of a given substance in terms of degree Kelvin, that can be multiplied with 1.21, then we are going to get it epsilon by k, and R value we are going to get it from here, and once if you get epsilon by k, you can calculate kt by epsilon AB, and once if you know the kt by epsilon AB, we can calculate f of kt by epsilon AB, and in this equation RAB is known, f of kt by epsilon AB is known, your molecular weights are known to us, the total pressure is known, temperature is known, everything is known, one can calculate the diffusion coefficient of component A in B. And according to this equation, if one can see, the diffusion coefficient is directly proportional to the temperature T to the power of 3 by 2, and it is inversely proportional to the 1 by P. Strictly speaking, this is not the exact relationship. If you look at this collision function, this collision function is also a function of temperature. So that means if you seriously look at the equation, your DAB is not exactly proportional to the T to the power of 3 by 2, it may be proportional to the 1.75. And maybe for the simple calculations, not to make a complex equations and other things, what one can say, DAB into P divided by T to the power of 3 by 2 is equal to constant. That means if I know the diffusion coefficient of component A in B at one pressure and one temperature, we can calculate the diffusion coefficient of component A in B at some other temperature and some other pressure. Or what we can say, DAB 1 PT1 divided by T1 to the 3 by 2 is equal to DAB 2 PT2 divided by T to the power of 3 by 2. So this is the expression one can use, and one can calculate. If I know the conditions at 1, That is, if I know the diffusion coefficient at conditions 1, I can calculate the diffusion coefficients at the condition 2. So this is generally we are going to use when we are going to solve the problems, or if I know the conditions at one condition at a location, maybe at point 1 where the pressure and temperatures are PT1 and T1, and if the new location is there where the pressure is the PT2, temperature is the T2, then one can use this equation for the calculations of new diffusion coefficients. So one can use this expression, that is the Wilkie equation, for the calculations of diffusion coefficient of A in B. If I know the temperature, pressure and molecular weights as well as the collision parameters, I can calculate the diffusion coefficient. Or according to this expression, if you look at seriously this expression, D is proportional to T to the power of 3 by 2 and inversely proportional to the 1 by P, inversely proportional to the P, or what I can say, if you are going to increase the pressure, the diffusion coefficient is going to be decreasing. If you are going to increase the temperature, the diffusion coefficient is going to be increasing, right? And this is the one way one can estimate theoretically if diffusion coefficient values are not known. Or what one can do sometimes, we are interested to estimate experimentally the diffusion coefficients, and if somebody wants to estimate the diffusion coefficient experimentally, then we have a twin bulb methods. We have a twin bulb method, or we have a Stefan's experiment and Stefan's experiment. In the case of gaseous systems, or in the most of the cases, people are going to follow the Stefan's experiments rather than the twin bulb method. So what we are going to do is, I am not going to discuss anything about the twin bulb method. If you are really interested to know about this, any book we can take on mass transfer operation where we can find out the twin bulb methods, whereas what we are going to do, we are going to discuss about the Stefan's experiment. So in the case of Stefan's experiment, we have a narrow vertical limb. This is connected with the horizontal tube. This is connected with the horizontal tube, and here we are going to take some volatile liquid, and here we are going to pass some gas B, and at time t is equal to 0, this distance is Z0, that is from this surface to the surface of the liquid, the distance is Z0. Now the gas is the pure gas, it doesn't contain any volatile liquids, so your PA2 is going to become 0, where A is nothing but your volatile liquid. Your A is nothing but a volatile liquid. This volatile liquid now contacted with the gas. So when we are going to contact your volatile liquid with the gas, now what happens? Volatile liquid, because it is having some vapor pressure, it will vaporizes, and when it vaporizes, it will join with the gas which is flowing here, and this gas is going to carry. We are going to adjust the flow rate of gas in such a way that always we can maintain that the partial pressure of the volatile liquid in the bulk of the gas is equal to 0, that is nothing but PA2. And if you see this surface, this is the surface which is formed between the gas and the liquid, and if the system is at a saturated conditions, there is a formation of the interface. At the interface, the partial pressure of the liquid is nothing but PA1, that is nothing but vapor pressure of liquid at given T. Do you understand or not? I have a narrow tube which is connected with the horizontal tube, narrow vertical tube which is connected with the horizontal tube, and this we have taken some liquid in the narrow tube. This narrow tube contains a liquid which is having some thickness, and to find out this thickness, which is the distance Z0 from the top of the things to the surface here, and the gas is continuously flowing, and there is a formation of the interface between the gas and the liquid, and if this interface is saturated, the meaning of that, the partial pressure of the volatile liquid in the gas at the interface is nothing but vapor pressure of the liquid at a given temperature. And we are going to maintain the pressure, we are going to maintain the flow rate of the gas in such a way that as soon as the liquid is evaporating, the evaporated liquid is carried by the gas B. So that means there is no concentration of liquid in the gas. So that is nothing but partial pressure of the A in the bulk of the gas is going to become 0. So because of this evaporation, at time t, if you are going to see, the liquid level is going to be drops to a new value is a Z1, and this distance we can call it as a delta G, right? Do you understand or not? Initially the liquid depth is Z0 from the top, and because of the evaporation of the liquid depth is falling down to Z1, and now in a given delta T time, the liquid depth is fallen to a value of delta Z, and a system again is going to come to the new steady state, and we don't really call it as a new steady state, we call it as a pseudo steady state approximation. In the case of pseudo steady state approximation, a system is, because the rate of evaporation of the liquid is very, very small, and we can assume that the pseudo steady state evaporation is going to be achieved. And if you look at this problem, the gas is not flowing down because there is no solubility of the gas in the liquid, whereas the liquid is evaporating and joining into the gas. That is nothing but a case like A through non-diffusing B case. So in this case of A through non-diffusing B case, already you know about the equation Na is equal to dAB into Pt divided by RT into Z Pb ln minus into Pa1 minus Pa2. This is the expression that we derived earlier. That is, when A through non-diffusing B is taking place, this is the expression that we have derived in the previous class. So in this expression, we know everything here. We know diffusion coefficient, that we have to estimate the diffusion coefficient. You know universal gas constant. We know the temperature. You know how much of drop that has occurred, and we know the total pressure. We know the logarithmic pressure of component B, and we know the partial pressure difference of component A and component T. Now, if you see at time t is equal to 0, Z is equal to Z0. At time t is equal to t, Z is equal to Z1. And how much of liquid that is evaporated, if you want to calculate that, that can be calculated by Na is equal to rho into m. Rho is the concentration, that is the mass concentration, kgs per meter cube, divided by molecular weight. We are going to get kg moles, we are going to get it, that multiplied with the dz by dt, right? This is kg moles per meter cube multiplied by meter per second. So 1 meter and meter cube, that is kg divided by kgs per kg mole into meter per second. That is going to becomes kg mole divided by meter square per second. This is nothing but a flux, and this is nothing but your Na. So that means your the dAB into dAB by RT by Z into PT by PB ln into Pa1 minus Pa2 is also equal to rho by m into dz by dt, where rho is the density of the liquid, m is the molecular weight of the liquid, Z is what is the distance that has fallen in a given time of t. What we can do using the boundary conditions, the boundary conditions are, these are the boundary conditions. Using this boundary condition, we can integrate this expression. And to integrate this expression, what we can do, integration of Z into dz, Z0, Z1. This is going to the other side. Then we are going to have dAB, PT, RT, PB ln MA divided by rho A into Pa1, Pa2 into dt, integration t is equal to 0, t is equal to t. And now if we can integrate this expression, and if we can bring dAB on one side, we are going to get dAB is equal to RT PBM rho A Z1 square Z0 square divided by 2 into PT into MA into PA1 minus PA2 multiplied by T. In this expression we know everything, that is in a given time of T, how much of distance that has fallen, the liquid distance has fallen, and we know the partial pressure of A, that is nothing but vapor pressure of liquid at a given temperature. Maybe we have an Antoine equation, or we have a general correlations where we can estimate the PA1 and PA2, that is the partial pressure of component A in the gas phase, that is going to become 0. We know the total pressure, we know the universal gas constant, we know the temperature, we know the density of the liquid, we know the molecular weight of the liquid, everything is known, one can calculate the diffusivity. And this is the Stephens experiment, and this is the experiment that we generally do in the laboratory for the estimations of the diffusion coefficients. And that is what I told you, we have a twin bulb method, or we have a Stephens experiment for the estimations of the diffusion coefficients. And those who are interested to know more about the estimations of diffusion coefficient by twin bulb method, they can take any book and we can find out the diffusion coefficient, or this is the one method where we have a Stephens expression and where we can find out the diffusion coefficients. Then in the last class, this is whatever the thing that we have discussed, it is applicable only for the gaseous systems. It is not applicable for the liquid systems. And when you talk about the liquid systems, as I told you again, the diffusion coefficients of liquids are available in the literature and for many of the liquids. And if suppose these diffusion coefficients are not available in the literature, maybe one has to use the again empirical equations, or the semi-empirical equations, or theoretical equations for the calculations of the diffusion coefficients. And as I told you already, the diffusion is very slow in the case of liquid when compared to the gaseous systems. In the gaseous systems, the order of the diffusion coefficient is in the range of 10 power minus 1, whereas in the case of liquids, the order of the diffusion coefficient is 10 power minus 5 meters square per second. And that shows about how slow the diffusion in the liquid systems. And we have one equation again, that equation, Wilkie-Chang equation. This Wilkie-Chang equation again given based on the Leland-Jones potential and kinetic theory of gases, your diffusivity of component A in the B in infinite dilution, where 0 indicates infinite dilution. That means the B quantity is very large, whereas the A quantity is very small. So infinite dilution of A in B dA is equal to 7.3 into 10 power minus 18 into pi into MB to the power of 0.5 into T divided by mu into VA to the power of 0.6. So where MB is the molecular weight of the solvent, T is the absolute temperature in degree Kelvin, and mu is the viscosity of the solution. Basically the solute is very small concentration, it is nothing but viscosity of the solvent, and VA is the molar volume of the A. And where now the new parameter that we are going to see is the pi, where pi is nothing but an association factor, and this association factor is the 2.26 for water as the liquid, and this value is equal to 1.9 for a methanol as a solvent, and this value is equal to 1.5 for ethanol, and this value is equal to 1 for non-polar solvents like benzene and ethyl ether, etc., etc. So this association factor are known to us, and that means your pi values are known to us. And the viscosity of the solution, as I told you, because the solution is very dilute, so viscosity of the solution is nothing but viscosity of the solvent. You know the viscosity of the solvent, and the VA is nothing but a molar volume, and this molar volume, solute molar volume, and this is in terms of a meter cube per mole. And once if you know that, we can take this, if you know what is the component A, we are talking about VA value is known, and one can estimate the diffusion coefficient of A in infinite dilution of B. And if you see this equation, DAB into mu divided by T is a constant. That means your viscosity of the solution is increasing, the diffusion coefficient is going to be decreasing. If temperature is increasing, the diffusion coefficient of component A in the B is going to be increasing, but here it is not, it is only of T, it is not a T to the power of 3.3 by 2, whereas for the gaseous systems it is a T to the power of 3 by 2, for various liquids it is only of T. Now, when you talk about strong solutions, the meaning of the strong solution is it is not a infinite dilute concentrations. If it is a strong solution, maybe 50% of A is there and 50% of B is there. If that is the case, and so 50% of A and 50% of B is there, that is the appreciable concentration of A and B is there. So DAB into mu is equal to DAB naught, that is a diffusion coefficient of A in B, where the concentration of A in the is a infinite concentration, multiplied by viscosity of A to the power of XA into dBA, infinite dilution of B in A, mu B to the power of 1 minus XA, and multiplied by 1 plus d ln gamma A by dXA, d ln gamma A by d ln XA. So this is the expression that one can use for the estimation of diffusion coefficients of A and B, where the concentrations of A and B are appreciable concentration, and to do that you need the infinite dilution infinite dilute diffusion coefficients at infinite dilutions, that is DAB naught, dBA naught, and viscosity of the A as well as the viscosity of the B, and XA and XB are the mole fractions of A in the solution. And here the new thing which is coming into the picture, that is nothing but ln gamma A by ln XA, where gamma A is nothing but activity coefficient, and this activity coefficient is given by PT into YA divided by PA into XA, where PT is the total pressure, YA is the mole fraction of A in the vapor phase, PA is nothing but vapor pressure of A at a given condition, XA is the mole fraction of A in the liquid state. So once if you know that, we are going to get activity coefficient, and this activity coefficient is a indication of how much of non-ideality we have there between the two solvents or two components. So your thermodynamics is going to give an information how to calculate the gamma A. Once if you know gamma A as a function of concentration, and we can find out what is, you can plot a graph between ln gamma A versus ln XA, and this will gives you the slope of d ln gamma A by d ln XA, and once if you know that, one can estimate the diffusion coefficient of A in B at any concentrations of A, and this is the way one can estimate the diffusion coefficients for the liquid systems. And there are, again, we can use some sort of experimental setup, and one can estimate the diffusion coefficients. Maybe what we are going to have a simple setup like this. Maybe here we have a porous disc, we have two chambers, we have two openings here to keep the component A, let's say, component B, and we are going to provide the stirring. We are going to provide the stirring here, and here the concentrations of A is more, the concentrations of B is more here. So, and this is the porous plate, because there is a concentration difference. The molecules of B is moving in the direction, the molecules of A is moving in the direction. When you stop the experiment at time t is equal to 0, you know what is the concentration of A here, what is the concentration of B here, and when you stop the experiment at time t is equal to t, we can take the concentrations and we can estimate the concentrations here, we can estimate the concentrations here. Once if you know these concentrations, one can calculate the diffusion coefficients. Maybe somebody is interested, again you can refer some advanced books where they are going to explain about how to estimate the diffusion coefficients of liquids A in B or B in A using this sort of a experimental setup. So this is what I want to explain you about the diffusion coefficients, and then what we are going to do, we are going to discuss about some numerical problems generally that we are going to come across in this molecular diffusion through the fluids. Just I am going to read for your purpose. We have a ammonia gas which is diffusing through the nitrogen. We have a ammonia, we have a nitrogen, and this ammonia is diffusing through the nitrogen. And under steady state condition, with nitrogen is the non-diffusing. The total pressure PT is given as 1.013 into the 10 power 5 pascals, and temperature is 298 degree Kelvin. The diffusion path is Z2 minus Z1, that is equal to Z, where Z is equal to 0.15 meters. And at location 1, let us say at location 2, at location 1, the partial pressure of ammonia at location 1 is equal to 1.5 into 10 power 4 pascals, and partial pressure of ammonia at location 2 is 10 power 4 pascals. Now the question is, we have to calculate the flux for the two conditions. One is non-diffusing B case, and then another one is the equimolar diffusion. So in the case of non-diffusing B, we know your Na is equal to DAB into PT RTZ 1 by PB ln into PA1 minus PA2. So we know one more equation according to the law of Dalton. The total pressure PT is equal to PA1 plus PB1, that is equal to PA2 plus PB2. So now PA1 is known, PA2 is known, total pressure is known, and we can calculate the PB1 and PB2. The PB1 is going to becomes 913 into 10 power 5, PA1 is equal to 863 10 power 5. This is the pascal, this is the pascals, right? Now PBM is equal to PB2 minus PB1 ln of PB2 by PB1. Substituting PB1 value, PB2 values, we are going to get 0.887. Now the flux Na is equal to 2.3 into 10 power minus 5 into 1.013 into 10 power 5 divided by 8.314 into 298 into 0.15 into 0.887 into 10 power 5 into 0.15 0.14 multiplied by 10.5. That is going to becomes 3.383 into 10 power minus 4 kilomole per. So this is for the non-diffusing B case. When you talk about the equimolar counter diffusion, for the equimolar counter diffusion case, we have Na is equal to DAB by RTZ PA1 minus PA2, that is equal to, plugging the values, 2.3 into 10 power minus 5, 8.314 into 298 into 0.15 multiplied by 0.05 into 10 power 5, that is equal to 3.09442 into 10 power minus 4 kilomoles per second. So this problem is clearly indicates how to calculate the flux for two cases, that is the equimolar counter diffusion case as well as the non-diffusing B case, where A and B we have, where both A and B are the gaseous components, right? Then we can discuss one problem on diffusion of A through B, where A and B are liquids. The problem is we have acetic acid which is diffusing through 1 millimeter film of non-diffusing B of water at 293 degree Kelvin. The concentration of acetic acid on one side of the film is 10% by weight and on the other side 3% by weight. The question is to determine the rate of diffusion of acetic acid. In this case, the value of diffusion coefficients of A in B is given by DAB, that is equal to 9.6 into 10 power minus 10 meter square per second, and the density of 10% acetic acid at 293 degree Kelvin is equal to 1011 kg per meter cube, and for 3% acetic acid it is 1003 kg per meter cube. So here what we have a 1 mm film, and here we have a water, we have acetic acid, here we have a 10% concentration, on the other side we have a 3% concentration, where water is not diffusing, the acetic acid is diffusing from higher concentration of 10% to the lower concentration of 3%, where thickness of the film is 1 mm, and density data are given, the diffusion coefficient values are given, and now you have to find out what is the flux of component A, where diffusion of A through non-diffusing B case, but here the systems are liquid systems, and as you know the flux can be estimated DAB by Z rho by M average XA1 XA2 divided by, right? In this case DAB value are given, the Z value is given, that is 1 mm means it is 10 power minus 3 meters. XA1 concentrations are given in the weight percentages, XP ln the concentration of B, weight percentages are given, but what you have to do, we have to convert into the mole percent. Then the density by molecular weight, because the solution contains both water as well as acetic acid. We have to calculate what is the average molecular weight at location 1, we have to calculate the average molecular weight at location 2, and the rho by M average can be calculated as rho by M at location 1, rho by M at location 2 divided by 2. So you have to calculate the concentrations in terms of mole fractions, and we have to calculate the average molecular weight at location 1 and average molecular weight at location 2. For this we are going to calculate the XA1, that is a mole fraction of acetic acid at location 1, can be calculated. We have 10 kgs. If you take a basis as 100 kgs, we have 10 kgs of acetic acid and we have 90 kgs of water. So the moles of acetic acid is a 10 by 60, that is moles of acetic acid, divided by total moles. 10 by 60 is acetic acid moles, and 90 by 18, that is the water moles. That is equal to 0.0322. So XB1 is equal to 1 minus XA1, that is nothing but 0.9678. So when you talk about XA2, similarly one can do 3 by 60 plus 97 by 18, that is equal to 0.0123. So XB2 is equal to 9877. XB2 is equal to 0.9877. So XB ln is equal to 0.9877 minus 0.9678 divided by ln of 0.9877 divided by 0.9678. That is going to becomes 0.977. Now you know the concentrations in terms of mole fractions, then you have to calculate the average molecular weight. Average molecular weight of 10% of acetic acid, if you take 1 kg as the basis, 1 kg contains 0.1 kg of acetic acid, 0.9 kgs of water. That is equal to average molecular weight of 10% acetic acid is equal to 1 divided by 0.1 by 60, 0.9 by 18. That is equal to 22.2 kgs per kg mole. Similarly, we can calculate for 3% acetic acid, that is going to becomes 19.68 kgs per kg mole. Then, so you know rho, that is 1011, you know 22.22, rho you know 1003, you know 19.68, everything can be plugged here and we can calculate 48.252 kgs per kg moles per meter cube. So you know rho by m average, you know concentrations, we know DAB. So now Na is equal to 94.283 into 10 power minus 8 kg moles per meter square per second. So this is the flux of A, that is acetic acid, through water when water is not diffusing, whereas acetic acid is diffusing, where the concentration of acetic acid 10% on one side, 3% on the other side, and we know the densities and the thickness of the film is 1 mm. So once if you know all those things, one can calculate the flux. So this flux we are going to use it for the design purposes, and I hope you understand both the problems, that is gaseous diffusion as well as the liquid diffusion. In the next class we will discuss some more problems related to the theory that we have discussed, so that you will be very clear about what we are doing exactly. Thank you very much.